I'm sorry. Start off. So last thing that we did combination of prisms and mirrors, and then we did images and stuff. So the next thing, there'll be a bit of a theory today. So, but important from mains perspective. Let's see, prisms. Others do keep your cams on. If your cams are not on, I'll be removing you from the classroom. So, and then, yeah. So what is a prism? Uh, Understand this derivation also because it is there in your board exam also. It is there in your HSC and CBSE. So you should know this. So a prism, right, is defined as it's made of a transparent material with at least two flat surfaces. So the most common one, right, that we take is an equilateral prism. So when you go to a lab and you take a prism, mostly it is an equilateral triangle. So then here we define something called angle of a prism. So what is an angle of a prism? Let's say light ray hits this surface and goes like this. Then we choose this to be the angle of prism. Suppose if the light ray hits here and goes like this, then this is your angle of prism. So depending on which two surfaces the light ray is hitting, the angle of the prism changes. Suppose if someone takes a hexagon, let's say light ray hits here, and goes off like this. Again, I'm exaggerating it. Then what you do, you extend the two surfaces on which the light ray is incident and refract, and that would be your angle of prism. Is that clear, everyone? So we define angle of prism as A is the angle between the surfaces where ray enters and ray leaves. Now, in exams like CET or even in mains, right? In the lab, the prism that you have is an equilateral prism. So A will be 60 degrees for everything. So in CET exam, if they don't tell you anything, generally it is an equilateral prism. So all angles will be 60. So it doesn't matter how you keep it. So when you go to IIT, right, in first year, you have a physics lab. They make you do this experiment. So basically, this is also comes under as an experiment. So this is an experiment to find the refractive index of the material. We'll talk about that. But everyone clear with this? What's a prism? So that's how you define it. It need not be a triangle every time. You can take any weird shape and you just extend the two lines and you can make a triangle. So listen to the geometry here. It's not tough. You should just know the thing derivation here. So this is your angle of prism. So let's say the light ray is entering here. This is your normal. And then the light ray goes like this and then comes out like this. This will be your another normal. So this angle will be your angle of incidence. This will be R1, this will be R2, and this will be E. E is the angle of emergence. Angle of incidence, E is angle of emergence. Now, if you see the geometry here, because that is normal, this angle will be 90 minus R1. This angle will be 90 minus R2. So in the upper triangle, A plus 90 minus R1 plus 90 minus R2 is 180. So this gives you A is equal to R1 plus R2. This is the first formula you should remember, where R1, R2 are the refracted angles inside. And now if you extend this, after the class gets over today or tomorrow, right? Just take a rough paper and just derive it on your own. It will help you to remember the results. This is your angle of incidence. This is the angle of emergence. So this light ray here would have gone straight. If there was nothing, you would have gone straight. And this thing has come back like this. So this angle here is delta, which is deviation. And now if you look at the angles, this guy is R1. So this angle is I minus R1. This angle was R2. This angle will be E minus R2. And now if you look at that whole triangle, we have I minus R1 plus E minus R2 must be equal to delta. Are you able to see that angle there? So the two interior angles will be equal to the exterior angle. In case you're wondering how, this angle will be 180 minus delta. So I minus R1 plus E minus R2 plus 180 minus delta is 180. So if you want, we can magnify this a bit. There. So that's your deviation. So if I arrange this, I'll get delta will be I plus E minus R1 plus R2. But R1 plus R2 is A. So delta is I plus E minus A. This is your second formula. Means if I is your incident angle, E is the emergent angle, and E is the angle of the prism, then the deviation is I plus E minus A. There, have a look at this. All clear with this? Any doubts on the angles, please ask. Great. Then, so we have delta is I plus E minus A. And also we can use Snell's law. The incident angle, let's say outside medium is mu M. Sin I will be mu of the prism sin R1. Mu medium sin R2. Sorry, mu prism sin R2. Mu medium sin E. Basically applied Snell's law here and applied Snell's law here. So here prism ka medium is mu P and I'm assuming outside is mu M and mu M. So there we also have our Snell's law. Now if you take a graph and if you try to plot this, now this is experimental. When you actually do a graph for this, deviation versus angle of incidence, you get something of this sort. This is not a parabola. It might give a feeling like this, but be careful, this is not a parabola. So this graph, right, if you see, it starts here. So what happens exactly here? At this point, you get a TIR. Meaning this light ray, after hitting here, it doesn't come out, it bounces off. So that is a critical case where the graph doesn't happen. So we are doing for a case where the light ray comes out. If there's a TIR inside, we can't use any of these formulas. Then you have to go back to the regular derivation. So that's the point where you get a TIR. Now, if you look at this, you will notice something. You actually get same deviation for two angles. You get deviation for this angle, and this angle, we get same deviation. So I and D are interchangeable. So if I and E are interchanged in this formula, you get the same deviation. So that is one thing. Means if you send with I, you'll come with E. If you send with E, you'll come with I. So I and E can be interchanged. So principle of reversibility. And now when you look at this point here, when I becomes equal to E, you get a minimum deviation. So the minimum deviation occurs when I becomes equal to E. Again, that you prove it from a graph only. There is, yeah, you can prove it mathematically, but becomes quite complex. You actually get it from the graph. You actually plot the whole thing and you do this experiment. So as you keep sending, when I becomes equal to, you get the minimum deviation. So over delta minimum, I becomes equal to E. This is another result you need to remember. That means delta minimum is 2I minus A. So from here we get I is equal to A plus delta minimum by 2. Then what is I? So put sin I here. And if I is equal to E, then R1 is also equal to R2. If I is equal to E, let me write that. This implies R1 is also equal to R2. This is also equal to A by 2. Perfect. So apply in the Snell's law there. So it will be mu m sin I is equal to mu prism sin R1. If I substitute here mu m sin I and I is also equal to E. So delta minimum 2I minus A. We get I is equal to A plus delta minimum by 2. So delta minimum you have to calculate from the graph. Now put it in the first Snell's law. Mu m sin I. I'll do it in the next page. I think this is a 4-mark question in boards. Mu m sin I is equal to mu prism sin R1. So sin I is sin A plus delta m by 2. You know A ka value. You know delta minimum from the graph. This is mu prism and R1 is nothing but sin A by 2. There. So we get mu prism by mu medium sin A plus delta minimum by 2 by sin A by 2. This is an experiment to find the refractive index of the prism. If the outside medium is vacuum, then mu m will be 1. If you have some medium there, it will be mu m. So that is how you can also take it. So this is an experiment to find refractive index of a material. Let me brief the whole thing once more. The main thing is getting the angles. And you should know that graph, right? When I is equal to it becomes minimum. There's no way out. Like, now see, I'll just show the whole thing what we did. We took a prism. We said this was A. You sent a light ray. This was normal. Light ray came like this. It came out like this. So this was angle of incidence. This was R1 and this was R2 and this was Z. If this was R1, this angle was 90 minus R1 and this angle was 90 minus R2. The sum of these three angles must be 180. So from there we got R1 plus R2 is equal to A. Then we said if you had extended this light ray and if you extended this light ray, the angle between them is deviation. This total angle was I. This was R1. So this angle will be I minus R1. This total angle was E and this angle was R2. So the balance angle will be E minus R2. And this angle will be 180 minus delta. Sum of these three angles, I minus R1 plus E minus R2 plus 180 minus delta is 180. 180, 180 goes off, you get I is equal to I plus E minus R1 plus R2. So delta will come I plus E minus A. And when you plot a graph for this, you get a curve like this. And you observe the minimum deviation occurs when I is equal to E. If I is equal to B, then R1 is equal to R2, which is equal to A by 2 because R1 plus R2 is A. Each angle will become half. Now from here I got I ka value, which is delta will be 2I minus A. So I found I ka value in terms of delta minimum, and I found R1 ka value. We take this and put it in Snell's law, mu m sin I is equal to mu prism sin R1. Substitute here, you'll get mu prism from here. Got the steps. I briefed up fast, but that's the whole process. Like if you're writing this for the board exam, you have to write the story. You just can't write the equations there. You have to tell this is the light ray, this is the deviation, and all that bullshit. Then you get 4 marks. But even for boards, mains level, it is important. You do get questions on this. All clear with this? Now, if R1 becomes equal to R2, something interesting happens there. So these are some theoretical equations again. So if you have a prism, let's say this angle is theta, this angle is also theta. Whenever you get a minimum deviation, the light ray becomes parallel inside the prism, which is true if you use an equilateral prism. Because for delta minimum, R1 becomes equal to R2 becomes equal to A, right? The light ray inside the prism becomes parallel to the base. There have been questions like this. If the light ray is parallel inside the base, the deviation is minimum, which is true for an equilateral or an isosceles prism. But let's say if these two angles are not same, theta 1 and theta 2, then it is not necessary. Then you can still have R1 is equal to R2, but still this light ray need not be parallel. So there is a statement question like this. A right-angled isosceles triangle is used in the experiment. Listen to the word. A right-angled isosceles triangle is used in the experiment. For the minimum deviation, will the light ray be parallel to the base? For delta minimum, will the ray be parallel to the base? What do you guys think? Now, if they say it must be always parallel, then you're gone. Maybe yes. Why? If you take a right angle prism, this is 90. If you take this is 45 and this is 45. But you can also take like this, isn't it? This is 90 and this is 45. I never told you how the light ray is hitting. So if you're hitting 45 and 45, yes, you'll be parallel. If you are hitting like this, then you won't be parallel. You're getting the case. They never said they're using the two angles 45 at the bottom. They simply said right angled isosceles. One can be 90, one can be 45. So in this case, the angle of the prism is 45. In this case, the angle of the prism is 90 degrees. Are you getting the catch? So the word right angled isosceles will give you a feeling, ha, ho jayega, but that's a trap. But in a lab, it is an equilateral prism. So you'll never have a problem because all are 60. No matter how you keep, it will be always parallel to the base. So in CET book, right, they write like that only. For minimum deviation, the light is always parallel to the base because they're using the thing in the lab. Clear with this? Next thing, condition for no emergence. This is also the case for maximum deviation. What I taught you now is minimum deviation till now. So this is a maximum deviation. This occurs when your angle of emergence becomes 90 degrees, meaning you're almost hitting a TIR there. You're entering, you're hitting, and you become parallel. This is a maximum deviation. So E becomes 90 degrees. This becomes theta critical. This becomes R1, and this becomes I. So basically, your R2 is theta critical. So they can ask you, when is the maximum deviation occur? So this occurs when E is equal to 90. And sine theta critical is 1 by mu. I'm taking outside 1. And we know R1 plus R2 is also equal to A. This is still valid. So R1 will be A minus theta critical. Apply the Snell's law. Sin I is equal to mu sine R1. So we get sine R1 is equal to mu sine A minus theta critical. So this is the maximum angle you can send. Anything more than this, the light ray will bounce. Sine inverse mu sine A minus theta critical. And this is another way of asking. What is the maximum angle of incidence so that the light ray comes from the other side? This is your TIRU condition. If I is greater than I max, there will be no emergent ray. So the ray will bounce here and it might come from here. We are not going to do that. This is your maximum deviation. All clear with this? Next thing, maximum angle of the prism. This is there in your CET book. I frankly never understood what the hell it means, but there's also something called maximum angle of the prism. But what it means, right? This is a weird case where your maximum deviation and minimum deviation occur at the same angle of incidence. So basically, there is only one angle at which you can send a light ray. You cannot send it any other angle. So the no emergence, that's your maximum deviation. And delta minimum occur at the same angle of incidence. So in a way, right, this thing is telling you what is the prism maximum angle you can have to do an experiment. So that's it. So mathematically, that's what it means. So what you're doing here, you're sending the light ray almost at 90 degrees. Since it is a minimum deviation, we are assuming it is isosceles, it becomes parallel, and then again it comes out like this. So your I is 90 degrees, your E is 90 degrees. This is theta critical. This is theta critical. So basically, there's only one light ray you can send. Any other angle, you're not going to come out. You won't enter or you won't come out. So here we can clearly see 2 times theta critical is A because that is R1 and R2. R1 and R2 is theta critical. So we get theta critical is A by 2, or you can say A is equal to 2 theta critical, and theta critical is sine inverse 1 by mu. And this is also called as maximum angle of the prism. So if the prism has more than this angle, the light ray will never enter. If it enters, it doesn't come out. Meaning that's the only thing you can think of in this. So this is called maximum angle of the prism. So total 3 cases: minimum deviation. For an isosceles prism at the base, the light ray becomes parallel. And this is the thing. Maximum deviation and maximum angle of the prism. All clear so far? That's it. That is the all theory for this thing. There is one case, thin prisms. Let me show you this also. We need this. What is a thin prism? Thin prism is a case where your angle of the prism is less than 5 degrees. Then what happens? Your mu, which is sine a plus delta m by 2 by sine a by 2, since a is small, everything is small. For small theta, sine theta becomes approximately theta. So mu becomes a plus delta by 2 by a by 2. If you simplify this, you get delta is equal to a into mu minus 1. There's an approximate formula for thin prisms. An important result. Comes a lot. Example, if you have a prism here, let's say mu is equal to 2 and the angle of prism is 3 degrees. So if you send a horizontal light ray, this will deviate. So delta will be A, which is 3 into 2 minus 1, which is 3 degrees. So this light ray here deviates by 3 degrees. There. That's your thin prism. Clear with this? You can copy down this formula if you need. You will need that formula. So again, how many formulas are there? A is equal to R1 plus R2. Delta is I plus E minus A. This delta is the normal deviation. The third, the graph is important. You should know the graph. I and D, two angles will give you same deviation. When I is equal to V, we get delta minimum. Third one is the graph. Fourth one is this formula, the mu of a prism. And also remember, this is an experiment to find a mu. The fifth one is this thing. Remember, the light ray becomes parallel to the base. The sixth one, no need to remember this formula, but if they say maximum deviation, understand E is 90, you can derive it. Angle of the prism, so ratta marna hi padega. These questions did come in the exam. And people didn't understand what do you mean by maximum angle of the prism. It is a case where a maximum and minimum deviation occur at only one angle. So there's only one angle you can send a light ray. And this is the minimum prism. So here only you have a 7 formulas here. 6 to 7 things you need to remember. Yeah, let's see a few questions on this. Questions are pretty straightforward. Matlab, just have a look at these things. Yeah, just try to read the question, try to do, and then look at the solution. Yeah, but advanced may also they do ask, so I'll show you a few. If the light ray doesn't come from that side and it bounces inside, forget about everything that I taught you. Just use regular Snell's law and solve the problem. All these formulas are valid only when you enter from one side and you come out from the other side. You should not bounce inside. But yeah, these are the standard formulas. See the first one? A light ray passes through an equilateral prism. Done. So he gave you A is equal to 60 degrees. The angle of incidence is equal to angle of emergence. So he said I is equal to E. And the later is equal to 3/4 of a prism. And he also gave I plus E is equal to 3 by 4A. Perfect. And if I is equal to E, that means R1 is equal to R2. सब हो गया ना, deviation का formula directly डाल दो. So delta is equal to I plus E minus A. I know I know E, I know A. Done. Make sense? That's it. There's nothing more to do there. Look at the next one. A prism of refractive index 1.53. So this is mu prism. is placed in a water of refractive index. This is mu medium. Angle of prism is 60 degrees. So this is A. Calculate the minimum deviation. Direct formula substitution. Mu prism by mu medium is equal to sine A plus delta m by 2 by sine A by 2. You know everything there. You'll get delta m from there. Yeah, if the angles they will give you if the numbers are weird. Sine 35.1 is 0.575. Easy stuff. Formula based questions. This will be CET questions. Now, if you take it a little better, this would have been an advanced question. Options are, let's give it a try. No, ABC is not the answer. They're just randomly marked. Try. This is a good one. So you have to take the graph and from there you have to figure it out. Think. Okay, let's see the data there. Okay, actually I got something. Let's try to figure out each one, okay? Look at the data here. Look at this point here. At the bottom, that is your delta minimum. And we know when delta minimum occurs, we know I is equal to E. So we know the formula delta is I plus E minus A. So just you can put the angle there. So delta is 60, I is equal to 60, E is equal to 60, therefore A. So A is also equal to 60. Is that making sense? That is one. Next thing. The refractive index का formula mu is equal to sine A का value now I know delta minimum by 2 by sine A by 2. A is 60, delta minimum is also 60. So this will be sine 60 by sine 30, which is root 3. So B is also right. Angle of incidence, he is asking. So basically he's asking this 41 degrees. He's asking this I1 ka value. So look at the value at I1. So I1 pe, the deviation is 63. But did you notice something here? You got the same deviation for two angles. And this I told you, you get deviation for two angles when I and E becomes interchanged. So basically, if this is your I, this should be your E because you're getting the same deviation. We get same deviation if I and E are interchanged, meaning if I send with I1, I'll get 63 degrees. Then 2I1 will be E. If I send with 2I1, I will get 63 degrees. Then E will be I1. So if I is I1, then E is 2I1. substitute in the formula. Delta is I plus E minus A. So deviation is 63. I is I1, E is 2I1, and this is 60 degrees. So we get I1 is equal to 41 degrees. So C is also right. What about D? In the above prism for angle of incidence of 70, now look at the value here. I1 is 41. That means this angle of emergence E here is how much? So 2I1 is 82 degrees. 82 degrees is giving you 63. 82 is giving 63, meaning 70 degrees would be somewhere here. It will definitely give less than 63, isn't it? Is that making sense? 2I1, 82 degrees gives delta 63 degrees. Therefore, if your deviation I is 70 degrees, then delta so must be less than 63 degrees. All four answers are right. Is that making sense, everyone? How we figured out all four? Just have a look at this. It's a good question. This is how they'll frame a multiple choice question. Understood what we did? Any doubts on any particular thing? So 82 degrees here was giving you 63. Anything less than that should give less than 63. So you can't have 65. That much we can figure out from there. Clear? Pratyasha? Shreyansh? Kashyap? Clear? Vedika? Akanksha? Aditi? Great. Now let's see one more. This I think is an advanced question. I don't remember. Integer. Now, looking at that, right, you can say, boss, you can't use anything about the prism. See, look at this, light ray is not coming out. So prism ka formulas are not valid. So just because you see a prism doesn't mean you have to use prism every time. So be careful with that. So none of the prism formulas will work. Do it normally. Use Snell's law. Give it a try. So the path of ray enters an equilateral prism. How much angle they didn't give. It is incident on PR at an angle slightly greater than theta critical. Matlab, you're hitting it theta critical only, almost. If the angle alpha shown in the figure is 30, this guy is 30. He's asking find the refractive index of the material. Yeah. Try. I'll give you 2 minutes. Could I show you? See, let's draw the picture here. So forget about this. This is A anyway. The ray is entering here. This is your normal. You're hitting here. This is the normal, and this is hitting here, and this is coming out. Great. Now he said you're hitting slightly greater than theta critical. So this is basically theta critical only. So theta critical plus zero point 0.1 degrees, something like that. Right, Aditi? Right. So it's an equilateral prism, equiangular prism. So yeah, so this is angle 60 degrees. Perfect. If that is 60, this will be 90 minus theta critical. Right. This is angle of incidence. So this angle will be 90 minus I. This angle is 30 degrees. Perfect. Let's get all the equations. So in that triangle, we have 90 minus theta critical plus 90 minus I plus 60 is equal to 180. So from here, we get theta critical plus I is equal to 60 degrees. This is equation 1. Then also, what is sine theta critical? Sine theta critical is 1 by mu. That's your equation 2. The third one, apply Snell's law, mu sine I is equal to sine 30. So mu sine I is equal to half. That's your equation 3. So we have these 3 equations. We have to solve for mu. Means I need to remove that sine theta critical there. Yeah, perfect. So let's substitute there. So what is sine I? I is 60 minus theta critical. So mu into sine I is equal to half. Sine I is nothing but 60 degrees minus theta critical. So this is nothing but sine A minus B. So this is sine 60 cos theta critical minus cos 60 sine theta critical is equal to half. And we know sine theta critical is 1 by mu. Cos theta critical is root over 1 minus sine square theta. So that's 1 by mu square. So that's root over mu square minus 1 by mu. Substitute everything here. Mu root 3 by 2. Cos theta critical is root over mu square 1 by mu. Cos 60 is half. Sine theta critical is 1 by mu is equal to half. Multiply mu inside, you get root by 3, root over mu square minus 1. This is minus half is equal to half. So root 3 root mu square minus 1 by 2 is equal to 1. Square on both sides. So 3 into mu square minus 1 is equal to 4. So mu square is equal to 7 by 3. Mu is root 7 by 3. He is asking mu is x by 3, x is 7. Clear with the steps? Yeah, right, Utsa. Right, Harshita. So the main thing is these 3 equations. Like I said, if the light ray has a TAR and comes off, don't use any of your regular prism formulas. Any doubts on this? So just because you see a prism doesn't mean you have to use prism formula. So just be careful with that. Let's see one more. So prisms they do ask in advance. Other than that, easy ones. This is actual and advanced. I think 2021 or 20. I don't remember the year. This is a PYQ. Let's get this. If you got this, I mean, your prisms are fine. Read. Take a minute to understand, and I'll explain. One thing I'll tell you. Instead of mu, he's calling it n. Bas, itna dhyan rakho. What we are calling as mu, he's calling it as n. So you can write this thing as d theta by d mu. Try. You got 2-3 minutes. So you are incident at a rate of 60 degrees on one face of an equilateral prism. The refractive index is n. From the other side, it emerges with theta. So he's saying if I keep changing the value of this refractive index mu, this theta also will keep changing. You're getting that? So indirectly is asking somehow find theta in terms of mu or find the rate of change of this angle with respect to refractive index. You're not changing the incident angle, you're changing the refractive index of the prism. Hope the question was clear. By changing mu, you can change the emergent angle theta. So he's saying for n is equal to root 3 and theta is equal to 60 degrees, find a rate of change of d theta by d mu, which he's calling as n. So I hope the question was clear. Try. Take a minute or two. It's an actual question. So great, Arshida. Yeah, one answer. Okay, let's see. Let's get the equations. So what all equations you have? Let this angle be R1, let this angle be R2. Yeah. So when you're entering here, this is sine 60 is equal to, I'll call it n, refractive index. So n into sine R1. That is one we have. And we also have R1 plus R2 is 60. That is the second one we have. The third one, mu sine R2 is equal to sine theta. Thus, we only have these three equations. Perfect. What you want is d theta by d mu. So d theta by d mu comes only from third equation. So differentiate this. If I differentiate this, I get mu. This will be cos R2 d R2 by d mu plus sine R2 is equal to, this will be cos theta d theta by d mu. There, that is where you get your d theta by dn from. I'll call it n, right? So this is n, this is n. There, that is where your d theta by dn is sitting. So differentiate with respect to mu. Great. So what all things I need? I know n ka value. He said root 3. R1, R2 I can figure out. R1 is equal to R2 is equal to 60. And what is R1 here for root 3? When n is root 3, this will be sine 60 is equal to root 3 sine R1. Yeah, R1 is 30 degrees. If R1 is 30, R2 is also 30. Perfect. Great. Let me use this in the next page. Perfect. Differentiate this also. dr1 by dn plus dr2 by dn is equal to 0 degrees. Perfect. So that will be dr1 by dn is minus dr2 by dn. So this is where I'll get dr2 by dn from. Differentiate this guy also. Basically differentiate all the three equations. Sine 60 ka differential is 0. This will be n. This will be cos r1 dr1 by dn plus sine r1 dn by dn, that is 1. So from here I get dr1 by dn is equal to minus n cos r1 by sine r1. Perfect. Substitute the values. N is root 3. That is 30 degrees. How much is that? Cot 30, right? Cos 30 by sine 30. This is minus 3. R1, R2 is how much? R1, R2 are 30 and 30, right? So root of 3. I think I wrote reverse. Sine R1 by cos R1. Still I did a mistake there and I got the answer right. So that is tan R1 and that's tan 30. Yeah, that is minus 1. Perfect. If this is minus 1, then dr2 by dn is 1. Now you have everything. Substitute here. So n is root 3. R2 is 30. dr2 by dn is 1. Sine R2 is sine 30. Theta is 60. Yeah, it looks a little lengthy because there are too many steps, but you got the idea there. How much is this? 3 by 2 plus 1 by 2. This is up. I'm getting a strong feeling I cooked up somewhere. That would be 2. I'm getting 4. Messed up somewhere. The answer is 2 actually. Where did I mess up? Yeah, most of you did get 2. This is a problem. N is root 3 cos 30. That is root 3 by 2. I think dr2 by dn I goofed up here, I guess. Yeah, how many mistakes I do, eh? This is 1 by n. This is minus 1 by 3. This is 1 by 3. This is 1 by 3. This is 1 by 2. There, that's your answer. Clear with this? So the basic idea is this. These are the three equations. That's it. At that point, physics got over. Differentiate all three of them. And differentiate all three of them. The first Geiger differential will give you this. From here, I get dr1 by dn. Differentiate the second one. From there, you get dr2 by dn. Differentiate the third one. You need dr2 by dn here. Substitute there, and you got it. Is the process clear, everyone? Clear with this? That's the idea there. So there, technically till here, we have it for advanced with prisms and everything. After this, we have something called dispersion and stuff and optical instruments. These are there only for mains perspective. They're not there for advanced, but bits may be here, CT may be here. That was one. Now, before going into that, I did a mistake. So we need to do that correction. We did this mistake here. This one. This was actually not a curve. Even I was surprised because I was doing a mistake there. That is actually a straight line. Let's see how we got that. So If you see the mirror curve formula, 1 by v plus 1 by u is 1 by f. If you divide everything by multiply by v, you get 1 plus v by u is equal to v by f. There's nothing, this becomes magnification. And magnification is nothing but v by f minus 1. This is nothing but height of the object by height of the image. So height of the image, which is your y coordinate, is height of the object, which is constant into v by f minus 1. You can take with the sign convention, minus h and everything. But if you observe this, so this is actually a straight line. The mistake I was doing, right? I was taking h of I as function of 1 by u. So the thing which we drew here, this guy actually goes in a straight line. Yeah, the arrows will lie on this, and this will go to infinity. Similarly, here also, this will be a straight line. So be careful with this. That's a mistake we did. It's actually a straight line. That means this thing is actually a trapezium. And this thing is also a straight line. All these are lines. Then the same thing when we did in lenses also, we have to change it there also now. So everywhere it was a line only. This was a straight line. This was also a line. That means that box actually forms a trapezium. So that's one correction there. So be careful with that stuff. Clear? That's one thing, be careful there. So that thing, the mistake was that you should not take with 1 by u because u is object distance. You should take x and y coordinate of the image only. So you should take hi plus as v. So that was there. Next thing. Now for this thing, right, which we took the prism, we have something called dispersion. So before that, we have something called Cauchy's formula. So what is Cauchy's formula? The refractive index mu not only depends on the material, it also depends on the wavelength. So for the same material, if you send a light ray of different wavelength, you get different refractive index. This is called Cauchy's formula. So here A and B are constants and lambda is the wavelength. That means you tell me if you send a red light and a blue light, which will have more refractive index? Who has more wavelength, red or blue? Red has higher wavelength, isn't it? 4,000 to 7,000 angstroms. So if red has more wavelength, red has more refractive index. So higher the mu, higher the lambda, higher the mu. So that means when you take a prism, thin prism, just now we derived the deviation delta is A into mu minus 1. So if you send a white light, again, I'm drawing a black line because I can't draw a white line here. If this is a white light, mu of red is greater than mu of blue or violet. Therefore, refractive index of red is greater than refractive index of violet. Therefore, deviation of red is greater than deviation of violet. Means if you send a white light through it, the red will deviate more, and the blue will deviate less. The two light rays will come out at different angles. They won't come out at the same angles. So if you send a white light, it has multiple wavelengths. This is how the picture will look like. There. I wrote reverse with delta deviation. This is going from. Array yaar, wait, did I write? Sorry. Higher the mu, higher the lambda, lower the mu. It is in denominator. Therefore, if lambda red is greater than this is reverse. So your blue will deviate more, the red will deviate less. Yeah, it is 1 by lambda square. So this is the reason when you send a light ray through a prism, right, the white light will actually split into multiple colors. And this is the whole concept behind the rainbow. So this phenomena of this light rays, coming out and spreading out, this is called dispersion. So this phenomenon of spreading light rays is called dispersion. Clear with this? Let me put few more pictures here. That's the there. Yeah, this is another graphical picture there. It looks good. That's a 3D prism that you send a white light, it starts spreading, and then it comes out like this. You must have done this in school with a scale, right? Sunlight is falling. You used to take a scale and put it in the sunlight, and you used to get 3 or 4 colors. So this is the whole idea there. So how does this work? So let's see. So that's how the picture looks. Again, this is a thin prism. I'm exaggerating it. So we will study the entire dispersion only for thin prisms. For whenever I say a white light, I'll be using a black line because I can't draw a white light here. So if you send a white light and this thing starts splitting inside, so red will be here, the blue will be here, all other colors will be in the middle. So this angle between them is called the dispersion angle. So if white light is passed through a prism, different wavelengths have different mu, so they all have different deviations. So all the light rays will deviate by different angles. So red will deviate the least and blue will deviate the maximum. So this is delta violet and this is delta red. This theta here we define is called dispersive angle. There, this is your first formula here after the Cauchy's formula. So dispersive angle is the difference between delta V minus delta red. And what is delta ka formula? A into mu minus 1. So this will be A into mu violet. So basically every color will have different refractive index. A into mu red minus 1. So this will give you A into mu violet minus mu R. This is your dispersive angle. This is your first formula. Clear this. And then we define something called dispersive power. This looks like omega, but it is not omega. This is called dispersive power. Dispersive power is your angle, dispersive angle by average deviation, delta average. So this would be delta violet minus delta red by delta average. Or sometimes if average is not available, we take yellow. Delta average or delta yellow. Either give me yellow or we'll take average. So here the formula will be delta V minus delta R. Delta average is delta violet plus delta R by 2. So if you substitute the formula here, you end up with mu violet minus mu R by average will be mu violet plus mu R by 2 minus 1. This is your dispersive power. So there, these are the two formulas which you should remember. Questions are rare, but there have been times they asked. Mu violet minus mu red by mu violet plus mu R 2 by 1. So that's your mu average. Clear with this? So I'll just put on the formulas here. See. So theta is A into mu violet minus mu red. The dispersive power is delta violet minus delta R by delta average. That's the simplest way to say, which is you can derive this mu violet minus 1, mu red minus 1. This is A into mu violet minus 1 plus A into mu red minus 1 by 2. A will cancel everywhere. You end up with mu violet minus mu R by mu violet plus mu R by 2 minus 1. That's how you got it. You need to remember there's no way out. Delta average is not equal to delta yellow. If it's not given, then we take it. All clear so far? And if you see only today's class, you have bunch of 10, 12 formulas already. This is the main idea in dispersion. So we will continue here, take a break, come back by 9:45. Any doubt so far? So come back in 5 minutes. It is not Srihari. I already told you. It's not. Delta yellow is need not be equal to delta average. Yeah, let's start off. Camps on everyone. Like I said, a lot of theory. You guys should revise this. Normally, I used to teach this at the end of the when portion gets over, and then your great seniors used to ignore it completely and don't remember anything, and means me aa jata tha questions. Better we'll do it little early so that you will have time. I will keep giving these questions in the weekend test that I'm conducting also, so that should help you to revise. So great, we got all the stuff. So how will the questions be? Questions are pretty straightforward, meaning they'll just give you the numbers, you have to put it there. Look at this question. Yeah, not this one. This one. There, just have a look at them. The angle of the prism is 10 degrees. I know it's not small, but yeah, that is the thing. Refractive index for red and violet are 1.51, 1.52. Find the dispersive power. The formula mu violet minus mu red by mu yellow minus 1. If yellow is not given, basically we take mu yellow as average, but which is not true every time. So you can take average. Substitute, you get the answer. Yeah, please go through everything. This is the level of the questions. Even at a mains level, this is how they'll ask you. The only thing you should know the formula. So prisms may we had 6 formulas. Here we have 2 formulas. So far 8. And your ray optics had another 14 formulas, I guess. So there's almost 22 till now. Look at the second one. The refractive indexes of a flint glass for red and violet are 1.64. So this is mu red and this is mu violet. The reason why we never k'd in ray optics, right? They change in like second decimal. So for us, it almost worked out. Find the dispersive power. Again, substitute in the formula and finish it off. In a certain spectrum produced by the glass prism, dispersive power is given. So the omega is given. It is found that mu r is 1.645, mu violet is 1.665. Find the refractive index for the yellow color of the light. So there. Now see, now they're not taking average. They assumed it to be mu yellow minus 1 and they calculated mu yellow separately. So if nothing is given, you can take that as mu average. But just be careful, it is not necessary that the average of red and violet is yellow. Bus. Are the questions clear, everyone? Straightforward formula substitution. You know the formula, dump it, you'll get your answer. So these are the 2 main formulas, the dispersive angle and the dispersive power. Now in this, there are 2 cases. If you take a prism and keep it upright, or if you take a prism and keep it inverted. So if you send a white light, blue will be this, the red will be this. But if you send it in an inverted one, they would reverse. Violet will be this, the red will be this. So now if you keep both of the prisms together, so this is called combination of prisms. Case 1, no average deviation, but there's a dispersion. So what this thing says is, if you take these two prisms, let this prism be A dash and let this prism be A. And now when you send a white light through this, it does split a bit. So this will be your violet. This will be your red. But if you take the average, the yellow, which you can't see here. Can you guys see that yellow? I also can't see basically. Maybe some dark color. This is better. This is yellow here, and this is the initial ray. These two are parallel. We say average deviation. So technically, we should not say it is zero, but your delta yellow is zero. So basically, the average of the delta R and delta violet, that will be parallel to the initial ray. So that's why we say average deviation is zero. So, but if you take individual letters, nothing is there. So the deviation will be delta 1 plus delta 2. Both the prisms will give 0. This is A into mu LO minus 1. That is the deviation of LO. A dash into mu LO dash minus 1 is equal to 0. So from here we get A dash is equal to minus A into mu LO minus 1 by mu LO dash minus 1. Negative indicates the prism is inverted. This is case 1. You'll never get 0 deviation. So what we do is we say average deviation is 0. So if you put two prisms, this is the initial ray and the yellow, they look as if it is parallel. Clear with this case? So delta 1 plus delta 2, the total deviation is 0. If I put three prisms, then it will be delta 1 plus delta 2 plus delta 3. You can just keep adding the deviations. Any doubts on this? Then case 2, no dispersion, but there is a deviation. Let me show you a picture. That is the best thing. I can't draw this. I think this one. Look at this. You send a white light, it will split into colors, then it falls on a prism, they again combine and get a white light out. So this is the case where there is no dispersion. White light is going, white light is coming out. But there is a deviation. So that's how the picture looks. This was that this is that average deviation wala picture. There's a dispersion, but there is no deviation. That's your average. So how does this work? We take two prisms. Let this be A and let this be A dash. You send white light. This thing splits and again combines, and again you get a white light. So this guy will have a dispersive angle theta, and this guy will have a dispersive angle theta dash. So the net dispersion is 0. So whatever angle you expand or spread, the same angle the other guy will compress. Theta plus theta dash is equal to 0. So what is theta ka formula? Delta violet minus delta red. For the second guy, it is delta violet dash because the material has changed. Delta r dash is 0. This is A into mu violet minus mu red. This is A dash into mu violet dash minus mu red. Now, frankly speaking, even I have a difficulty remembering this, but I know how to derive them. It doesn't take more time, but you should know. I think the stuff is there in CBSE board exams also. I'm not sure. So if you have this angle of the prism, then there'll be no dispersion. If you send white light, you'll get white light out. Clear with these two cases? So this is a combination of prisms. Average deviation is 0, no dispersion there. So no other process. And this is how they'll frame questions on this. There, just have a look at this. So combination of two prisms, one flint and other crown glass. They produce dispersion without a deviation. That is case 1. The angle of the flint glass is 15. Calculate the angle of the crown glass prism and the angular dispersion of the red and the violet. Meaning he's taking case 1 and he's that asking deviation is not there. Okay, but in that there's a dispersion, right? How much is that? Dispersion is theta plus theta dash. Try. Think for a minute, like, and I'll show you. See what he's saying. So there are two prisms. One prism angle is 15. Great. The other prism we don't know. And he's saying they are producing dispersion, but there is no deviation. So delta plus delta dash is 0. Mu is given for both of them. So first thing, deviation is 0. So what is the deviation formula? A into mu minus 1, A dash into mu dash minus 1. From here, we calculated A dash ka value. So that is the first thing. Deviation delta plus delta dash is 0. Why say second prism ka angle aa gaya. Now he is asking, agreed, there is no deviation, but there's a dispersion. Basically, he is asking, this guy and this guy are parallel. There is no deviation, but this light ray got spread out. What is this dispersion angle? So this first prism will give theta, the second guy will give theta dash. So we add both of them. So the total dispersion, this is theta plus theta dash is theta net. And what is theta? A into mu violet minus mu red. This is A dash into mu violet dash minus mu red dash. So we got A dash from the first part. So we have to use this angle here. And then, yeah, they gave the omega also, 0.2 and 0.03. Substitute here. And done. So meaning the angle between the red and the violet is 0.975 degrees. So there is a dispersion. The light rays did spread out, but the average deviation is zero. Play with this. So this is how they'll combine stuff and ask you equations. So if you know the formulas, you are done. Even if you don't, you should know how to be able to derive. Clear with this? The next thing, chromatic aberration. In this, there's only one important formula which you should definitely mug up. This did come up in multiple exams. Aberration, you heard this word before, spherical aberration in mirrors. Spherical aberration. Aberration means errors. It is because of being a spherical. Chromatic aberration meaning, think of it like this. Suppose if you take a lens, we know 1 by focal length of a lens is mu lens by mu medium minus 1 by 1 by R1 minus 1 by R2. And just now we said the wavelength is different. So mu red is less than mu violet. So therefore, your focal length f red is greater than f violet because it is 1 by f. So if you send a white light through a lens, everyone will have different focal length. Till now, we never had a problem because we always sent monochromat. So that means if you actually try to take a photograph with a camera, when the light falls on it, you actually get errors. The image will get distorted, the colors will get mixed up and everything. So how do we solve this? So if you send a white light, the focal length of red is more. That means the blue will meet earlier. The red will go even little farther. So the image you will get will be a distorted image. You won't get a proper image. This is your aberration. This is happening chromatic basically because of the wavelength. So this error is called chromatic aberration. So how do we solve this? We use two lenses. So this is called achromatic combination. The idea is this. If I use a biconvex lens and if I use a biconcave lens, now see what happens. So when you send parallel rays, we are saying the violet will be here. These guys will go like this. So when you extend them, the violet will be here. The red will be here. The red will be here. Because it appears to meet there. So here f is negative. So focal length is negative. Now, if I combine both of them in such a way, now see what is happening. This biconvex is pushing the red more forward. This biconcave is pushing the red backward. If I combine these two in such a way, that thing gets cancelled out exactly. Now, when you send a light ray, now everything will meet at one single point. This is called an achromatic combination. So if this thing has focal length f1, this thing has focal length f2, which is negative here. F1, F2, and omega 1 and omega 2 are dispersive power of the lenses. Now, we don't need the derivation here. So the idea is this, the divergence of biconcave and the convergence of convex, they add up. They cancel out. So for this to work, the dispersive power omega 1 by F1 plus omega 2 by F2 must be 0. And 1 by F equivalent is 1 by F1 plus 1 by F2. So this whole thing will act like a lens of F equivalent here. And be careful, F1 is positive because it is biconvex there, and F2 is negative. You have to substitute with the sign. Very important. Definitely remember this. In this entire prism ka thing, which I taught you, dispersion and all that stuff, if you can't remember for some reason, at least remember this. I have seen this coming in CET, mains, Vellore, Manipal exam. Direct question they'll give you. In an achromatic combination, they'll start the question like this. In achromatic combination, the focal length of one lens is 20 centimeters and the dispersive powers are 0.2 and 0.3. What is the focal length of the other lens? Pass ho gaya question. And what is the equivalent focal length? So omega 1 by F1 plus omega 2 by F2 is 0. You'll get F2 from there. Then 1 by F equivalent is 1 by F1 plus 1 by F2. Very important standard result. You should definitely know this. This is dispersion. All clear with this? The next thing, optical instruments. Now in this primarily we have two things, microscope and a telescope. Again, we have certain results. You should know how it works also. This thing is technically there for mains, but this can be also made into a paragraph and asked in advance. So that way it is important. You should know how it works. So what is an optical instrument? So first of all, you should understand how human eyes work. When you see something, what do you think you're actually seeing? We humans cannot see lengths. What we see is always angles. Think about it. Like the screen in front of you or the finger, which is bigger? The laptop screen and the finger, which is bigger? The laptop is bigger, right? You know that. But take the finger and put it near the eye. The finger looks much bigger than your laptop, isn't it? The building in front of your house looks smaller compared to your finger in front of your eye. So what you're seeing is not the length. We humans cannot see length. What we're seeing is always angles. So human eyes and cameras, right? They always detect angles. Same way, we can never see velocity. We always see angular velocity. Remember that? We discussed in circular motion. Think about it. If you're going in a train, which is going with the speed of 50 kilometers per hour, so train is going with 50 kilometers per hour. If there is a tree here, A, and if there is a tree here, B, did you ever notice the person nearby feels like going faster compared to the person who is very far? When you're going on your car or a bus, did you ever see the road? It feels like the road is going very fast. But think about it logically. If your vehicle is going with speed 50, relative motion, this is also going with 50, this is also going with 50. So shouldn't both of them look like they're going with same speed? But what happens is this. In time t, they travel same distance, agreed. But if you look at the angles, look at this. B will cover less angle compared to A. So you think the objects which are far are actually rotating slower. We humans cannot see velocity. What we see is angular velocity. We are angular creatures. We don't see anything in linear. We can't see lengths. We can't see speeds. What you see is angular speeds and angles. So when I tell you to look at a rod, you're actually looking at the angle subtended. So that's the main idea there. So you should know how an eye works there. So human eyes and cameras, they see angles subtended by the object. So listen to the stuff. The explanation is important. The derivations are important. So let's say if you have an object here, 10 meters, and let's say this is pretty far, 100 meters. And let's say we have an object of 20 meters, and let's say this distance is 500 meters. So now if you look at the angle here, this angle is theta 1. So tan theta 1 approximately equal to theta 1 is 1 by 10. This is theta 2, tan theta 2 approximately equal to theta 2, which is 1 by 25. So if you see here, even though the 20 meters is bigger, it feels the 10 meter looks big. So theta 1 is greater than theta 2. Therefore, the 10 meter looks bigger than 20 meter. This is the problem with the eye. What you see is always the angles. So this is the first thing, okay? This is how human eyes work. Second thing, we have another problem. Distance of least vision. If something is very close, you can't see. Try to look at your nose. You'll get a headache. If you try to focus too much, you'll get a headache. If you try to see, right, you know there is something there, you can't see your nose. It looks like there is some frog or something there. So there is something there. You just can't see your nose. So this is called distance of least vision. If something comes too close, you can't see this. We represent this with capital D. Generally, this distance is 25 centimeters for adult. Kids have it even less, but as time passes, this thing increases. This is the minimum distance up to which eyes can focus on the object. If you keep anything closer than this, you can't see. Up to which eyes can focus on the object. So there, first thing we see angle, second thing you can't see if you're too close. D ka value is generally 25 centimeters. If they don't give anything, always check 25. These 2 points are clear. So basically, this is the main theme there. Now, so if you have an object height h and the distance is capital D, this angle theta naught. So theta naught h, the height of the object by D, this is the maximum angle you can see without an instrument. This is the maximum angle without an instrument. So when you look at an object, this is the maximum angle you can see. So as you bring the object closer and closer, you start seeing it better. So we define angular magnification M as theta by theta naught, which is the angle seen by the instrument. So if you use an instrument and if you see a bigger angle, this is how your magnifying glass works. By angle without instrument. So this is defined as your magnification. Great. These are the basics there. So the first device we have is a simple microscope. Just put your hand little far, right? Can you look at your fingerprints? Just put your hand little far and look at the fingerprints. Can you see them? Put it little far, like stretch your hand and then look at the hand. Can you see your fingerprints? Now, if you bring them close, if you keep bringing them closer and closer and closer, just get your finger closer and closer. You will see the fingerprints. Get little more close, you will see. Get little more close, you can't see. Once you bring too close, less than 25 centimeters, suddenly it goes off out of focus. You can't see anymore. Now, the reason why you can see, right? The fingerprints, the two fine lines you have, when you are very far, the angle they're subtending is very small. As you bring closer and closer and closer, they're subtending bigger and bigger angles, isn't it? Human eyes can see up to 0.6 seconds. 60 seconds is 1 degree. Human eyes are that sensitive. If there are 2 points making an angle of 0.6 seconds, which is 60 seconds is 1 degree, you can tell them these are two different things. But if the angle becomes less than 0.6, you think it is a dot. Let's see, I'll show you. I'm zooming this. This is 1000. So this is a point. These are 2 points, right? Still 2 points. Still 2 points. Still kind of looks like 2 points. Now, you can't even see the point, right? It's here. Can you see? अभी दिख रहा point? If I zoom out, there you can see 2 points. If I keep zooming in, it starts looking like a single point. If I go more, it is here actually. You can't tell anymore. You get the point there. Those are actually still 2 points. Nothing changed. So the angle subtended is a problem. So that's how it works. So what you're looking at is always the angles. So how do we overcome this thing? See, the problem is simple. If you bring it close, you get big angle, you can see clear. Awesome. But if you bring it too close, you can't see. That is a problem. So what a simple microscope does, a simple microscope is simply a biconvex lens. That's it. It is a single lens. And look at the idea. If you know how to do this, you'll remember. So we take a biconvex lens, put it in front of an object. So this is the object height h. We keep it at a distance u. So this light ray passes through the optical center. And you have to keep this object between pole and focus. The object has to be placed between the focus and the pole. That means you get a virtual image. This light ray which goes here will go off like this. So when you extend them, this is the image. And this distance is v. So see what we did. And if you look at the angle subtended, this is your angle theta, which is actually still the same. If you look at angle theta, which is height of the image by v, which is also equal to height of the object by u, which is h by u. So basically, when you put a prism in front of it, you're not actually changing the angle. See what happened, I'll tell you again. So just under this thing. Meaning, if you look into my screen, right, you have a finger, you bring it close, I can see. Bring it close, I can see big. Bring it close, I can't see. Right? But angle is still bigger. So what I did now, I took a lens and kept it in between the object and my eyes. When I did that, what happened? I got an image little far, isn't it? So what you did, you didn't change the angle, you made the image go far. Now suddenly that image is more than capital D. Now you can suddenly see this. Are you getting what does a microscope do? Microscope does not change the angle. It increases the distance of the image. So the more closer you bring, the image also goes far. So you can actually see it more clearly. So a few precautions you have to take here. The object is between focus and pole. It should be a virtual image. The image is virtual, erect, and magnified. Now from the definition, the magnification, m is given by theta naught. So theta is h by u. Theta naught is h by d. That is the image distance without magnification, d by u. So the magnification of a simple microscope is given by d by u, where d is the distance of least vision and u is the object distance. That's your main formula in a simple microscope. Is the idea clear what we did? So when you put a microscope in front of an object, you're not increasing the angle bigger. What you're doing, the angle became bigger because you brought it close. But you brought it so close, you are unable to see it. Did you ever see this? CST, if you go now, there are some people there who write your name on rice ka grain. They do paintings on a rice ka grain. Kabhi dekha aisa? There are artists who do that. They take one rice ka grain, on top of it, they draw a picture. So you really can't see that, right? You have to bring it very close. If you bring this close to the eye, you can't see. So you put a microscope in the middle, telescope in the middle, a microscope. So the image goes far. Is the idea clear? Now in this, there are two cases. Case one is called normal adjustment. Normally, when they ask questions, they'll ask you in these two cases only. There's a case called normal adjustment or far point. Quite an important word. Far point implies the image is at infinity. That is, rays are parallel. Why do you need to keep the image at infinity? Because what happens, right? When your eyes are looking something very far, your eyes are in a very relaxed state. Now think about it. If you're a scientist and working on a microscope for 3-4 hours, you don't want your eyes to get strained. Kabhi aapne observe kiya? If you looking at something very small for long, within 5-10 minutes, your eyes get really strained. But if you look into the sky for 10 hours, nothing happens. When you're sitting outdoor and looking into the sky for half an hour, half a day, one day, nothing happens. Because when light is coming from very far, your eye muscles are relaxed. The natural, when the letters come parallel, right, they actually go and meet on the retina exactly. So your eye is in a completely relaxed state. But whenever you look at something very small or very far, your eyes have to focus. So that means your ciliary muscles, which are actually taking care of your eye, they are under strain. Your eyes get stressed out. So generally, when you design an equipment, you want to design it in a normal adjustment. This is what is called as normal adjustment or far point. The image is at infinity. So this keeps your eyes relaxed. So if the image is at infinity, means U is equal to F. So the magnification is D by F, where F is the focal length of the lens. So in this scenario, eyes are least strained. You can work on this equipment for hours and nothing happens. Another extreme case, case 2, is called near point. This is a bad design, but this is the other extreme case. In this case, what you're doing, you're putting the object in such a way the image is at the distance of least vision. Means it is on the border of your vision. If it just moves a little, you can't see anymore. Image forms at a distance of least vision. So it's almost on the verge of not being able to see. So your eyes are really strained a lot. So then we get V is equal to minus D. Apply the formula for a lens. 1 by V minus 1 by U is 1 by F. These are the kind of things they can ask in advance as a paragraph. 1 by D by 1 by U is 1 by F. So 1 by U is 1 by F plus minus 1 by D minus 1 by F. The magnification is D by U, which is 1 plus D by F. There, this is the other magnification. Just take the magnitude. So you actually get little more magnification. So if you use in a near point, you get little more magnification, but eye is maximum strained. You won't be able to work for long. So that means in a simple microscope, your magnification can lie between 1 plus D by F and D by F, where F is the focal length. This is your simple microscope. Is everyone clear with the working? So the whole story starts with 2 points. One, humans will see angles. Second, if you bring something very close, you can't see. The more closer you bring, the bigger the angle, good. But if you bring too close, once you cross 25 centimeters, you can't see. So that's a problem. So how does a simple microscope solve the problem? You bring it too close, you can't see. But when you put a lens there, the image becomes virtual. So it feels as if the object is far. You're making the object go far. The distance has increased. You never actually changed the angle. So you get a magnification there, which is D by U. In this, we have two cases, normal adjustment and near point. Normal adjustment or a far point is a case where the image forms at infinity. Near point is a case when the image forms at capital D. Capital D is the thing when your vision is almost on a blur. Clear with this? Let me show you a question how they'll ask. A convex lens of focal length 20 centimeter is used as a reading glass. Capital D is 25 centimeters, which is the distance of least vision. That's again a new term, everyone. Terminology is important. Find the closest and the farthest. At which a person can read a book. So there's a book in front of you and you have a reading glass. Using this glass, you're trying to read the book. The distance of least vision is 25. Means if you put anything less than 25, you can't see. How will you do this question? Matlab, think. Not a tough question, but that whole wording and the way it is framed, right? You'll feel like, what the hell? Matlab, how do I even start? This is a kind of a question that came in the exam. Think for a minute, I'll tell you. You are using a reading glass of focal 20 centimeters. Think of like this. When you look into the sky, you can see stars which are very far. So if you have nothing in front of you, if you don't have any microscope, you can see any object which is between infinity and capital D, technically. But if I use a lens, yeah, I can see infinity also, but I can see something very close also. Yeah, Srihari, you have better eyes than most people then. If someone can see less than 25 centimeters, then you have good eyes. That's why you don't have glasses also, I guess. I also have glasses. So if you remove the glasses, I can't even see who is there in front of me. I can't even recognize myself in the mirror. Forget about looking at someone else. See, the idea is this in this question. So what you're looking is actually not the book. When you use a lens, you're looking at the image of the book, isn't it? Remember that when you put a lens in front of something, you're always looking at the image. So this image can form anywhere. The image can form, so the image of the book. So what you're looking at is image of the book. You're not looking at that book directly. Image of the book can be between infinity. You can look when it is at infinity. That's how you look at stars in the sky. They're at infinity. Yeah, you can't read them, but there is something there. Hypothetical case, and 25 centimeters. So if the image is less than 25, you can't see. So these are the two extreme cases. The image should be infinity to 25. So if image is at infinity, this is the near point ka case, the normal adjustment. That means your object must be at the focal length. U is equal to f, 20 centimeters. So when you keep the book at focus, you will get a light rays are at infinity. So your eyes will be kind of relaxed. Image is at D, 25 centimeters. That means V is minus 25. Apply the lens formula, 1 by V minus 1 by U is 1 by F. So 1 by U will be minus 1 by 25 minus 1 by 20. How much is this? Take out 1 by 5 common, 1 by 4 plus 1 by 5. That's 9 by 100. U will be minus 100 by 9. This is minus. So basically, it is behind. So your object must lie between 20 centimeters and 100 by 9 centimeters, which is close to 11.11. So you should keep the object between this range, or else you can't see the image only. Right, Anvita. Got this thing? Now, these questions are not tough, but if you have not seen anything like this before, exam mein idea aayega nahi. So the main headache with these things are that you should have seen these questions once, and then it is manageable. Clear with this? That's your simple microscope. After this, we have a compound microscope and a telescope. So the idea is the same, right? So I think we will do that in the next class. It won't take much time. I think it'll take another 20-25 minutes. We will finish it off. And next class, we'll start off with the waves. We'll be starting off with waves on a string and sound waves in the thing. So, but yeah, I know today's class, there's a lot of theory and a lot of stuff. And this all mains ka stuff, dispersion, ray optical, optical instrument. Optical instruments can be still asked in advance as a paragraph. So, but you have a bunch of formulas. I'll send you a small sheet on this, not much, maybe 15, 20, 30 questions on this. That much is sufficient so that you remember. Yeah. Okay, I think that will wrap up for the day. So when we see on Thursday, we'll continue with this. A little part is left, but ray optics is officially done at an advanced level. So please start solving. We have done almost 50 questions. Finish it off. Take a week deadline by next Thursday. Try to finish off solving everything. And if you have already done your material, I sent you a sheet. I hope you have seen that. So 70, 75 questions are there of advance. You can give it a try. Okay, with that, we'll wrap up for the day. I'll see you guys on Thursday. We'll continue from here. So, any doubts, anything else, please stay back or else you're free to leave. And do remember there's a test online on Friday. Make sure to give it.